Good morning, everyone. My name is Qi Zhang. I'm a PhD student in 3D Media Group of Temple University in Finland. Today, in this presentation, I'm going to talk about our analysis of optical aberrations in a light field display, and we'll propose a calibration approach to enhance light field display performance. As many of you are aware, light field technology is a fascinating way to capture and represent both spatial and angular dimensions of light rays in space. A light field display is designed to replicate light field of a 3D scene, generating multiple views of the scene to the observer. Specifically, if in a light field display, multiple scene perspectives are rendered within the size of an eye pupil, it will produce dynamic accommodation, or in other words, the eye can naturally focus on objects at varying depths of the rendered scene, much like it does in the real world. This diagram provides a detailed illustration of how a light field display ideally creates a focusing effect for the eye. In the model shown here, the light field display consists of a display input panel and an optics component. Together, they generate a light field model with two key planes, the virtual display plane, which is the image plane of the display input, and the viewpoint plane. Positioned beyond the viewpoint plane is an idealized model of the human eye. Let's consider a scenario where we want to render a specific point in space. To do this, we activate 3 pixels on the display input plane, each corresponding to one of the 3 viewpoints. Rays start from these 3 pixels, propagate through their virtual display points, and go towards the respective viewpoints. These rays intersect precisely at the point in space we aim to render. As the eye changes focus, the retina captures the image like slices at different depths, recording where the 3 ray footprints are. When the eye shifts focus from far to near, these footprints draw close together, perfectly overlapping at the exact depths of the rendered point, and then diverge again. From the observer's perspective, this translates to the image quality shift from blurry to sharp, then blurry again, with the sharpest focus achieved at the exact depths of the rendered point. This is the focusing effect we expect. In the ideal scenario, the optics are free of aberration and always propagate as intended. But what happens in practical displays where aberrations are present? In our previous experiments, we encountered this issue. We were working with a time-multiplexed near-eye light field display testbed developed in collaboration with the Swiss company Serial. This setup featured a 6x6 viewpoint grid with the size of a pupil. Our goal was to test the focusing effect of this system. We did this by rendering a test chart at a specific depth and capturing its focal stacked images using a camera equipped with a focus-tunable lens. The image quality was assessed by calculating the Spatial Frequency Response, or SFR, from the captured images. Interestingly, our test results were almost in line with the expected focusing effect. However, we noted that the best SFR was achieved at a depth shift from the actual depth of the rendered chart. Also, when we compared with the overall SFR performances with the simulated ideal case, where optical aberrations are excluded and only diffraction limit is considered, we found that our test result is quite constrained. We suspect that the practical aberration of our test setup might be one of the source of these errors. It's worth noting that in our case, the SFR of a single viewpoint image seemed barely affected by the aberration. This leads us to wonder what else would be influencing the result. This study continues from here. Apart from the factor that optical aberration will degrade the single viewpoint image, though not much in our case, it is crucial to consider that the final observed image is actually a superposition of all these viewpoint images. If the superposition process is disrupted, it can lead to significant issues in the overall image performance. To better understand this, let's look at the relocations in the diagram again. This is what happens in ideal case, And this is what occurs when we factor in aberrations. Due to aberrations, the correspondence from the display input to the virtual display plane changes. The distance between the virtual display and the viewpoint plane might vary across the field because the virtual display plane might not be a flat plane anymore, but rather a curved surface. Also in practice, the actual location of the viewpoints might deviate from their intended design. Wavelengths will also affect ray propagation behaviors. All these factors contribute to what we call the literal shift of rays, or more formally, transverse ray aberrations. This term describes the deviation of ray locations compared with to an ideal scenario. To address this, we propose a method to characterize these transverse ray aberrations and then compensate for them by pre-distorting the original input images. Our aim is to achieve the correct focusing effect, just as we would expect in ideal case. To understand and characterize transverse ray aberrations, we've developed a display retina image formation model. In this diagram, we replace the simple block in our previous diagram with a practical display optics. For example, here, it's a magnifier lens stack. This stack projects the display input panel onto a virtual display with a zoom ratio. Let's start with an ideal scenario. Consider an ideal pixel P in on the display input. It's first imaged onto the virtual display and then through a viewpoint located at V, and the final location of this point P out is on the retina. This setup leads us to an equation that connects the display input and the retina output, incorporating viewpoint locations and other display-related parameters and eye-related parameters. This equation implies that the final image of the retina is essentially a zoomed version of the input image with two central shift terms. And one of these central shift terms includes the eye's focal length. In an ideal aberration-free system, the display-relevant parameters are predefined. They remain constant and don't vary with viewpoint locations, wavelengths, or input pixel locations. However, in the real world where aberrations are present, this is not the case. These parameters are actually vary depending on the wavelengths, viewpoints, and input pixel coordinates. Along with the viewpoint locations, these parameters are unknown and need to be determined. That's the part marked in red. Fortunately, inspired by varifocal cameras, we've found a way to calibrate these parameters. We do this by taking focal stack images of a specific input chart. Then, using the analytical solution showed here, we can calibrate these parameters. In our ideal scenario, with predefined parameters, we can achieve the expected output using the ideal input. We can pre-distort the original ideal input from P in to a new position, P hat in. This pre-distortion is designed to compensate the real transverse ray aberrations, allowing us to achieve the result comparable to our ideal case. By combining these equations for both the ideal and the real scenarios, we can determine the amount by which we need to offset the input pixel. This offset varies for each wavelength and each viewpoint and is dependent on the input pixel location. We've taken steps to validate our approach by incorporating both calibration and correction processes into light field display observation pipeline. All of this work is currently being done through simulation models in DMAX. We start by calibrating the real model in our simulation. Then we aim to render a simple 3D scene, basically at one point in space. And based on an ideal model, we determine the input for each viewpoint. These inputs are then corrected to compensate for aberrations. We observe the results of our display using a varifocal camera, still within a simulation environment. This simulation is based on geometric ray tracing, so the captured images reflect footprint patterns of ray samples. Finally, we conduct some analysis and processing of the captured images and to help us to evaluate the effectiveness of our calibration and correction processes. Here are some more key aspects of the simulation model. The real display optics in our simulation include aberrations and consist of 6 practical lens models. While it is a hypothetical model, it closely resembles our actual test setup. The ideal model represents the target display model we aim to achieve. It has predefined parameters, for instance, the magnification ratio and the distance between the virtual display plane and the viewpoint plane. The display input area is the effective area for us we define for calibration. The viewpoint in our simulation is artificially shifted to appear irregular, differing from our practical setup. We use an ideal camera model with a fixed back focal distance. During the simulation, the only change we make is to its focal length. And for the ray tracing and recording, for each infinitely small pixel on the display plane, we sample 1009 pixels uniformly across each viewpoint. This means we trace 1009 rays emanating from one input pixel. We then record the footprint of these rays on the sensor as the focus changes. This process is repeated for 3 different wavelengths and across 6 by 6, 36 viewpoints. We begin by looking at the calibration input and sensor output. Essentially, what we are working with is an 11 by 17 point grid covering the effective display input area. The sensor output captures the pattern of the rays. These are recorded along 3 key dimensions: focus, viewpoint, and wavelength. This is a calibration result. First is the viewpoints. The red crosses represent the calibrated viewpoints. They align exactly with the ground truth locations that we originally set in the simulation. This is a calibrated result of parameter A. To illustrate how A changes, we include 3 sets of images. Each set is designed to show the variation of A in relation to 3 different factors: the spatial location of input pixel, the viewpoint, and the varying wavelength. For context and comparison, a plane marked with dotted lines in the first figure represents the value of A in the ideal model. You can see in the ideal model, it's like constant and independent to other factors. Similarly, we've observed the calibrated parameters C, just as we did with parameter Z. The insights we gain from both parameters A and C are that the single viewpoint image will experience deformation, and this deformation varies with different wavelengths and viewpoints. It's also important to note that the deformation isn't just about the changes in the shape of the image. It also involves variation in the offsets of the centers, just as the parameters C. With the parameters we've calibrated, we're able to pre-distort the images we input. Now our objective here is to render a 3D point along the optical axis positioned at 1 diopter relative to the observing camera. To do this, we start with 36 viewpoint images. Each of these images, only a single perfect pixel is activated. For each viewpoint and each wavelength, we then pre-distort these images, which serves as the corrected input for the display. Then, by tracing rays in our simulation, we finally obtained the ray footprints for all wavelengths and viewpoints in each of the focal stacked images. In this slide, we compile these 11 focal stacked images ranging from 0.5 diopters to 1.5 diopters into an animation. It visually demonstrates the effect across the different focal distance. Here, we have the animation in the middle in corrected case. On the left side for comparison, we're also showing an animation with uncorrected input synchronized with the corrected one. As we anticipated, in the corrected case, the footprint patterns from different viewpoints and different wavelengths follow a proper trend. Here they come close together and then diverge. Notably, the center of the patterns overlap perfectly when the camera focuses at the depth of 1 diopter. Since evaluating image quality solely based on the ray patterns isn't common, we converted these patterns into observed point spread functions, or PSFs. We then use these to calculate the modulation transfer function, MTF. For each wavelength, we identify the central location of each footprint and shift the corresponding elementary PSF to these locations. We simplify this processing by using the central elementary PSF, the PSF of a central input pixel, rather than the exact local PSFs. Then we aggregate all the spatial shifted elementary PSFs across all wavelengths, assigning them equal weight. This approach yields the polychromatic PSF, or the observed PSF on the sensor. Finally, by applying a Fourier transform, we obtain the final observed optical transfer function, or OTF, and MTF at a specific focal depth. This is the animation showing the observed PSF as it changes focus in the corrected case in the middle. On the left, it's the uncorrected case. It might not be immediately obvious when comparing them, but if it has the same color bar for both. So it's still noticeable that the PSF on the left appears more spread out and its peak is much dimmer. This animation shows MTF as focal depth changes is more straightforward. You will see the MTF in the middle, the MTF curve rise, peak at the exact focal depth, and then decline. In contrast, for the uncorrected case on the left, this trend is less pronounced. It appears that the MTF consistently decreases. To further analyze this, we use a threshold value of 0.1 for all the MTFs. With this benchmark, we examine how the cutoff frequency behaves during the focus change. This figure illustrates our findings. The vertical line represents the depth at which the point is rendered in our simulation. The solid curve shows how the cutoff frequency changes along with the focus in the corrected case. In contrast, the dashed line presents the cutoff frequency behavior in the uncorrected case. Here we have a compilation of all the final results. We separately render points both on axis and off axis at depths of 0.2D, 1 diopter, and 2 diopters. So six points separately are simulated. In this figure, we'll plotted the cutoff frequencies at a value of 0.1 in the observed MTFs. The dashed dot line at the bottom represents the off-axis result, while the dashed line represents the on-axis result. Both are under uncorrected cases. The solid line with crossed markers indicates the corresponding corrected results in off-axis case, which is almost completely overlap with the on-axis corrected results in solid lines. So this figure validates our approach. By using predistorted display input, we achieve proper focusing. Moreover, at each focal depth, the image performance in a corrected case is markedly improved comparing with the uncorrected ones. In this figure, we've also included a series of bold dotted curves. These represent the cutoff frequencies in ideal cases, where only diffraction limitation of the viewpoint size is considered. Interestingly, we observed an anomaly. When rendering a point at 0.2 diopters, the corrected cutoff frequency actually surpasses that of the ideal case. We believe that this might be due to the reason that the effect viewpoint size of the combined display and the camera system in our simulation model changes as the camera adjusts its focal length. The viewpoint size increases when the camera focuses on deeper depths and decreases for shallower depths. As a result, the image performance in ideal settings in our simulation can be better than in an ideal model with always fixed viewpoint size. We are currently conducting further studies to verify these hypotheses. Let's summarize our key findings and look ahead. Firstly, we've established that transverse ray aberration significantly impacts the observed performance of light field displays. To address this, we proposed a calibration approach specifically for transverse ray aberration. By predistorting the input images for display, we effectively compensate for these aberrations. This adjustment has shown a notable improvement in the observed performance, enhancing both the MTF and the focusing effect. Looking to the future, our next step is to practically apply this application method to our light field display setup. This will be crucial in further refining our approach and achieving even better display performance. So that's the last slide of my presentation. Thank you for your attention.